Okay, so we begin this video with a theorem, and the theorem essentially says that the educated guess that we made in our last video was right. So if we have a system like this, where it's a 2 by 2 linear system, A is a real valued matrix, it has one real eigenvalue lambda, but only one independent eigenvector. So we don't have enough to build all of our solutions. The general solution is going to have this form. It's y equals e to the lambda t times some vector v naught plus t e to the lambda t times some vector v1. Very different from when we have two solutions built out of eigenvectors where we have arbitrary constants in front of each piece. The constants are going to show up as the components of these vectors. Okay. Because it's going to be the case that v naught, this vector here, is just going to be the vector giving us our initial condition, the x and the y values at time t equals 0. v1 will be a minus lambda I times v naught. Okay. Further, v1 is either the 0 vector or it's an eigenvector. Now, I'm not going to prove this theorem. Okay. If you're interested in proving it, we can work on that in office hours, or you can make that an exercise for yourself. Basically, what you have to do is just take something of this form, plug it into both sides, and see that you actually get the same thing. So it's a kind of involved calculation, but it's just plug in and verify sort of thing. Okay. I will point out the fact that v1 is either 0 or an eigenvector is not something that would need to be proved. It's just, this is just, by the way, this is true. This falls out from advanced linear algebra. Okay, so that's a consequence of advanced linear algebra that probably even those of you in linear algebra aren't going to see this semester. Okay, what I want to do instead of prove this is I want to get back to our initial problem. I want to look at the phase portrait because we found our general solution to this problem, but we didn't look at the phase portrait, and I want to know what that looks like. So let's recall what the problem was, because oh my goodness, we've had so much going on, and isn't it fun to watch me erase the board? Oh. Okay, so we were looking at y equals -2, 1, 0, -2 times y. We had that lambda was our only eigenvalue was -2, and the only eigenvector we had, the only independent one we had, was 1, 0. Any non-zero multiple of that is another eigenvector, but it won't give me something independent. Okay. So I want to try to draw the phase portrait. And once again, I can draw the phase portrait without knowing the general solution. So do be careful to read the directions. If you're asked to find the general solution, do. If you're asked to find the phase portrait, do. If you're asked to do both, do. But one is not necessary for the other. We can find the general solution by just doing algebra. We can find the phase portrait. We need to do some parts of finding things. We need to find our eigenvalues and our eigenvectors. But we do not, in this case, need to go ahead and find the general solution because that is not explicitly built out of the eigenvalues and the eigenvectors the way it is if I have enough independent eigenvectors to build things. So I'm going to say, okay, here's my phase plane. Here's x and y. I know I've got my equilibrium solution. Now I also know that I'm going to have some straight line solutions. So I'm going to go ahead and draw those. So I'm going to have 1, 0, and that just basically determines the x-axis. And so the right half and the left half of the x-axis are equilibrium solution, or straight line solutions rather. And those will be approaching the origin because my eigenvalue is negative. Okay. So the straight line solutions divide the plane up into two parts, the top half and the bottom half. And I want to get a representative solution in each region. Okay. Now, what that's going to look like, I want to sort of think about this when I have one eigenvalue. That's kind of the boundary between having two real eigenvalues and having none. Now, when I have two real eigenvalues, I would have two straight line solutions. That would divide the plane up into 4 pieces, and I would then calculate a solution or estimate a solution in each of those regions. But if I have no eigenvalues, that's when I get this spiraling behavior. Okay. So if I have one eigenvalue and not enough eigenvectors, and I'm a solution curve up here, here's my thought process. I want to spiral. I want to spiral around that equilibrium solution, but I can't because a linear system like this always satisfies existence and uniqueness, and so solution curves can't cross. So my solutions are going to look like things that start to spiral and then get trapped by the straight line solution and are going to approach the origin. They will be approaching the origin, which is a sink because my only eigenvalue is a -1, okay? And they'll be approaching it then asymptotic to the straight line solutions. So at this point, it's actually very similar to what we've seen, losing my train of thought, with the spiral sources and the spiral sinks and the centers, that I want to know what direction it's trying to spiral in. If it's actually spiraling, I need to know whether it's clockwise or counterclockwise. Here, I need to know the same thing. It's just not going to succeed in actually spiraling. Okay. So I usually plug in a point either on the x or the y-axis. Here, plugging in a point on the x-axis would be most foolish, as that would be on my straight line solution. So I'm just going to plug in 1, 0, and I'm going to say, what is the derivative there? So if I look at -2, 1, 0, -2 times 0, 1, that's this point here. I may have just said 1, 0 a minute ago. I meant 0, 1. Okay. That's going to give me 1, -2. Remember, the shortcut is this just gives me the second component, the second column of my vector. So at this point, the tangent vector is going in this direction, over 1 and down 2, more like so. Something like so. Okay. That means we're trying to spiral clockwise. Okay. So I want to draw a solution that tries to spiral clockwise, but is prevented from doing so by the straight line solution. So I'm going to have something like so that's coming in with that as its tangent, but then it has to turn to approach things like so. And then I'd have sort of a mirror image on the other side, wanting to spiral in a clockwise direction, but not being able to cross that equilibrium solution, so having to curve to avoid it and approach the origin that way instead. Okay. Okay, to keep this vector here because I've got it in a different color, so it's clearly not part of my solution curve. Maybe I'll actually even draw it as a dotted line. You do want to, when you pick a test point to see the direction of the derivative vector, you want to respect that. So I tried to make that tangent to my solution curve as I was coming in. You do want to respect that, but do make sure that it doesn't look like that's another straight line solution because it's